Welcome back to the drawing board presented by TBPi, where today we're going to be covering orbitals and electron configuration. So what is an orbital? Simply stated, it's a shell that holds two electrons within it. These two electrons then sit around the nucleus in many different ways depending on what your orbital looks like, and we'll get into that all later. But all you need to know for now is that they hold electrons. So you find these orbitals within energy levels and subshells. So energy levels are probably what you've seen before on a model of an atom. Those circles around the nucleus generally will look something like that. So each one of these little circles here, this is what's known as an energy level. Essentially, an energy level tells us how much energy is in an electron. So the ones that are closer into the center, those are going to have lower energy than ones near the outside. Inside those energy levels are subshells, and those we call N, P, D, and F. We'll get to those a little bit later, but essentially those subshells are going to tell us what these orbitals look like around the atom, or the nucleus of the atom. Finally, our use for orbitals is they help us to locate electrons. So electrons are very random, they move completely randomly except when we look at their orbitals. They're often held into these orbitals and we can at least get a better estimation of where they're going to be. So now that we know a little bit about the orbitals, what are some ways that we look at orbitals, like within atom itself? So this is a very old model that we looked at a second ago. This is called the Bohr model of the atom. Essentially this just shows us these rings around a nucleus in the center. So it's not all that helpful for us and extremely inaccurate, but what it does show is those energy levels that we talked about. So this innermost ring right here, this is our first energy level, would be level 1. And the second here, that's our second energy level, level 2. Of course, those can all fill up with different numbers of electrons based on their orbitals that we'll take a look at in a second. Another model that we have that's pretty widely accepted today is the cloud diagram. So I know it doesn't look like much right now, but what we can see is it's darkestly colored here in the center and less more towards the outside of the atom. So the idea is this is trying to predict where we will find an electron. Near the center, where it is darker, there's a much better chance we're going to find an electron there because there's the most energy there, it's the lowest energy levels. There's a good chance we'll find them. And here towards the outside, it's very rare we're going to find them. So why do these electrons move around like this? It all has to do with the energy inside of an atom and of an electron itself. So the easiest way to look at it is to look at a very simple atom of helium here. So it's simple, nucleus, 2 electrons, they would both be in the first energy level. So what happens is if we have a little photon here, which is essentially a little energy unit, if we take that photon, attach it to our electron here, it goes in what we call an excited state. And it moves from this inner ring to the outer ring. So as it does that, it becomes a part of this outer ring, and we now call that in the excited state. So now that it's in the excited state, it's further away from that central nucleus. So that's why we have the probability that those electrons will travel further away. But naturally, it's going to eventually have to come back to its original state, which we call the ground state. So in order to do that, our little electron here is going to shed that energy back off that little photon, whether that's by light or releasing heat or something along that line, and it's going to move its way back from out here back inside to its ground state and back to where it started. So while it is much more probable we will find an electron on the inside here, we could also find it on the outside. So hence why a cloud diagram makes sense for the current model of an atom. So the other way we can look at atoms is to look at their subshells and within that their orbitals. So drawn here you see the 4 different subshells. The S subshell, the P, the D, and the F. So they're all slightly different, so we'll go through them all. So first of all, the S subshell holds 2 electrons, and it just looks like a big sphere around our central nucleus here. So it's just a sphere, it holds 2 electrons in it, it's as simple as it gets. A p orbital, or a p subshell, holds 6 electrons. And along with this sphere, which is in the center there, it's kind of hard to see, we also get these 2 big lobes on the outside. And those are also 2 more orbitals. So while the S subshell had 1 orbital, the p subshell has 2 orbitals like this, plus the central orbital that looks exactly like the S one. So that has a total of 6 electrons, 2 per orbital. So 2 here, and then 2 in the center. Next we have our D subshell. That can hold 10 electrons. So it's the same idea as the p subshell, except now we have 4 orbitals around the outside, plus that central s orbital. So 2, 2, 2, 2, and then 2 electrons in the center, gives us a total of 10. The f orbital holds 14 electrons. I can't draw it. We'll put a picture of the f orbital up on screen here. It follows the same idea as the p subshell and the d subshell. So it holds 2 electrons in every single one of its orbitals. It just now has more than both the p and the d for a total of 7 orbitals. So now that we know all about orbitals, what can we do with them? So as we said earlier, their main purpose is so we can estimate where we can find an electron. So in order to know that, we need to know which orbital it's in and where within that orbital it sits. So in order to show that, we use something called an electron configuration. So it's pretty simple. It's just a number, a letter, and then a number. And of course, they all represent something. So this first number, this 2 in our case, represents our energy level. So you remember we were talking about energy levels earlier with that first diagram of the atom that we showed, the Bohr model. And each one of these rings right here represents a different energy level. So knowing that, that's the first piece we need to know to find an electron. Second thing we need to know is the subshell. So that is this P here, also known as the subshell. So if you remember when we were going through, we had the S, the P, the D, and the F. So being a P, we now know what the orbital looks like that we will find our electron. And finally, this 4 is the electron number within the subshell. So in this case, we have electron 4, so it's the 4th electron within the P subshell. So what can we do with these electron configurations? We know how they look, of course, like this, 1s2 and 2p2, whatever, but how are we going to use that to identify different substances, like carbon in this case? Well, what's really cool is we can use the periodic table to kind of be our guide for how we're going to fill this out. So if we look really closely, our carbon sits right here on the table, but more importantly, as a table as a whole, it has a very distinct shape. And while that does have to do with how we lay out elements, what's also very cool is each row of the periodic table can kind of represent an energy level for us. And that kind of goes the same for each of the groups or the columns that represents a subshell. So we know this block right here, all the stuff, the left of this line right here, that is all S block. So everything on the left there, that's always going to represent our S block. This group right here, so all these elements to the right, these represent our P block. So there usually be 6 of them, but ours is drawn a little crude here, so we don't quite have that many. But usually this would be our P6 portion. Right here in the center, these transition metals, this is our D section. We have 10 of those. Then down here, these little guys everyone always forgets about, this is our F block. There are 14 of those. So you might notice we have this weird little helium hanging out here. This would usually be the element helium. And hydrogen, which also doesn't have complete S. So what we do in this case is we just take our helium, goes on a little ride over here. And for our case, we put helium over here next to hydrogen as part of the S block. So let's take a look at our carbon again. So our carbon's down here and we want an electron configuration for it. So we can go through the periodic table to find out how we're going to get that. So we always start in the top left corner up here, and these are our first 2 electrons here in the S block. So that's 1, and then in the S block, and then there are 2 of them. So that's our 1s2 right here at the top. So unfortunately, that's it for row 1. So then we'll go down to row 2, or the second energy level, where once again, we'll start in our S, where once again, we have 2. So that's our 2s2. And then we go over here. So now we go into the P block, where carbon is the second one over. So we're going to call that 2 for second energy level, P for P block, and then 2 for 2 electrons in there. So that makes our electron configuration for carbon 1s2, 2s2, 2p2. So that notation we just wrote that in was called standard notation. That's where we go down and we write every single one of these. So 1s2, 2s2, 2p2, all the way down to whatever element you're working with. But there are other ways we can notate this. So one of them is the noble gas notation. So what makes this nice is we can skip all the energy levels before and go straight to the nearest noble gas and then only go on from there. In this case, we would go down to helium, being the closest ideal gas without going beyond carbon, and then we just have to do the 2s2 and the 2p6. So we would be able to skip everything before that. Finally, we have orbital notation. So, not gonna lie to you guys, orbital notation gets a little annoying, but it gives us a really good look at how the electrons within the atom are working. So what we do is we take our standard notation, so our 1s, our 2s, and our 2p, but we leave that last number out, and we draw a line on top of each one to represent its orbitals. So for the S block, we do 1 line, For the p block, we do 3 lines since it has 3 orbitals. And then we draw these little arrows here to represent our electrons. So each orbital can hold 2 electrons, so we have 2 arrows. You'll see they're going in opposite directions. This has to do with the spin of the electron. So everyone that's going up has a spin in a certain direction, and everyone going down has a spin in the opposite direction. You'll also notice in our 2p orbital here, since we had carbon, we only needed 6. So we didn't fully fill up this p orbital. So what we did instead is dropped 1 electron in each orbital that we could. In our case, that was these first 2, and left the third one blank. And then we did not put any electrons spinning the other way. So we're always going to fill each orbital with 1 electron before adding the second one in. So let's try an example of these electron configurations. So the problem says here to write the electron configuration of germanium in all the methods, or all the notations, however you want to say it. So what we know about germanium is it is atomic number 32. So that means we're going to need to fit a total of 32 electrons into our electron configuration. So we're going to start just like we did for carbon. So we'll start with our first energy level. Always start with the s orbital, and we have 2 electrons in there. So if you pull back out our periodic table, that's all there is on the first level. So we're done with the first energy level. So let's go on to the second one, 2. And then of course we always start with the s, and that always has 2 electrons in it, all right? And of course the second energy level also has a p block, and that can hold up to 6 electrons. That's 2p6. So far we've used 2 electrons here and 8 electrons here. So we are not yet at 32, so we need to keep going. So then we're going to add on our third energy level. So looking back, our third energy level is identical to our second energy level. So we're just going to go ahead and do the exact same thing we did for this one. 3s2 and 3p6. So we now have 18 electrons accounted for, not at 32. Not even close, so we're going to keep going. So we'll go to our fourth energy level now, start with our X block, and now we run into something a little strange. Now we run into our D block here right in the middle. So naturally, you would be thinking that after 4s2 would come 4d10. Unfortunately, that is not at all how this works. This is probably the weirdest thing about this concept. Instead of 4d10, this is what we call the 3d10 block. It doesn't make a lot of sense. It's just kind of how it works. So if we look now, so that's added 12 onto our previous total of 18. So that would put us at 30 total electrons that we've used thus far. So that means in our next block, which will be our 4p block, we are going to hit our germanium. So since we are at 30, we need 2 more. That would make this a 4p2 block. So that right there is our electron configuration for germanium in standard form. So now let's go to the easy one, and my personal favorite, the noble gas notation. So germanium is beneath argon and above krypton. Argon is atomic number 18 and krypton is atomic number 36. So since we fall between those, we have to use the one before, so we'll use argon. So we start by putting argon in the brackets here. So that argon essentially lets us skip all this stuff up here. So we can jump straight down to our last row here. And then we'll just repeat what we did over here. 4s2, 3d10, and 4p2. And that's it. That's our noble gas notation. Finally, we'll do our orbital notation. So this is where orbital notation gets a little hard to work with. So we'll start drawing it all out here. So we have our 1s, our 2s, our 2p, 3 of course, 3s has 1, 3p has 3, 4s has 1, then we go to 3d, which has 5 orbitals, and finally our 4p, which has 3. So we have all our orbitals drawn out. Now we've got to go add electrons. So of course, always fill up first, then down. Same down here. And when we're going through the p's, make sure you fill all in one direction first, then go back and get all your ones going in the other direction. Same thing through these blocks. As we know, all the lower energy levels are filled if we are up to the higher energy levels. So our 4s block here, that's completely full. It's 4s2. Our 3d block, that's full since it's 3d10. So we'll go ahead and draw in all those. And now we get to our 4p. So we have 4p2. So going through just how we drew the other ones, 1, 2. And that is our orbital notation, noble gas notation, and standard form for the configuration of germanium. All right, so now we'll do one more example that's very similar to the last one. So this one we're going to find the electron configuration of lead with a minus charge in standard form. So that's great. We only need standard form, so we only have to do about a third of the work we did last time. So we'll start out exactly the same as we did. Atomic number for lead is 82. However, we do not need 82 electrons because this isn't an atom. This is an ion. It has that minus charge. That minus charge means we have one more electron than the atomic number. So we'll add 1 to our 82, we'll get 83. So that is our target number, is 83 electrons. So now that we have that, we'll just go through like we did before on the previous problem. 1s2. After that, we go down to our second energy level, 2s2, 2p6, down to our third energy level, 3s2, 3p6, and then down to our fourth, 4s2. Now don't forget your 3d10 and 4p6. All right, so unfortunately, we're nowhere near 83 yet. We would be at 36 electrons at this point, so that's not 83, so we'll have to go to our next energy level. It's going to be 5s2, 4d10, so that d block goes up a number, but should still be one behind our s and p, and 5p6. So adding those on, we get up to 54 electrons, but we're not at 83 yet, so we'll keep going. Start out with 6s2, and then we come back to one of those funky spots like before that we had with the D. So after 6s2 comes in these little guys down here. These elements that nobody cares about but are part of the table, and we need to take them into account here. So they sit right here and right here. So after that 6s2 right here, we have to go and get an F14. So this is called our 4F14 block. So we'll put that in next. Then we'll put our D in. So that puts us to 5D10. And finally we have our last P block, but we're getting close to our 83 now. So in order to get to 83, we need another 3 electrons. So instead of making this 6P6, we'll make this 6P3. And that's how you get it in standard form for lead with a minus charge. So now that we know about orbitals and electron configurations, we can talk about quantum numbers. So when we're talking about things that are quantum, we're usually talking about quantum mechanics. So real brief overview of quantum mechanics. Essentially, we don't really know where something is going to be, so we take a guess saying it could be in one of many states. Now picking these states is really complex, we're not going to worry about that, but for what we need to know is we want to identify what these states are. Now quantum mechanics could be a whole series of videos in and of itself, so go research that on your own if you're interested, but what we're going to worry about today is quantum numbers of electrons. So each electron has 4 quantum numbers: our energy number, our angular momentum number, our magnetic number, and our spin number. So what do those all represent? So let's go through them one at a time. Starting out, we have our energy number. This is denoted by the letter N, and this simply represents our energy level. So it would come directly off our electron configuration. So just 1, 2, 3, 4, all the way up. That is as easy as it gets, and that will be the first quantum number we write down as we go through. So it would be N. Next one we go through is L, and this is our angular momentum number. And what this takes into account is the shape of the orbital itself within the energy level. So this essentially talks about our block, our S block, our P block, our D block, and our F block. And whichever one of those blocks we're in is going to assign an angular momentum number, L. Next we have our magnetic number. And this has to do with the specific orbital we are within inside of our block. So if we are in our P block, but we are in the circular orbital, instead of one of the 2 lobes on the outside, that'll be accounted for in this magnetic number. So this ranges from negative L, which is whichever one we are in, all the way up to positive L. So since S is 0 in our L's, that means we would go from negative 0 to 0, so the only magnetic number we would have is 0. But if we were in the P, that would give us 1 in our angular momentum. That means you'd be able to go from negative 1, 0 to 1 in our magnetic number. And that comes after the L. Finally, we have our spin number. So remember how we said there can be 2 different electrons in each orbital? Those are designated by the spin number. It's always either negative 1/2 or positive 1/2, depending on which way the electron is spinning. That is our final number we give. If you can give N, L, M1, and M2, then you have completely said where you think you can find a specific electron. So let's do an example that has to do with finding those quantum numbers. So in our example here, we need to find the quantum number for the 10th electron of aluminum. So when we say 10th electron, all we mean is as you're going down the electron configuration, so 1s2, 2s2, 2p6, and down from there, so on to 3s2, and so on and so on. We're looking for the 10th electron out of these. So this would be electrons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what we care about is the electron that's in the configuration 1s2, 2s2, 2p6. So that's the electron we care about. The fact that it's in aluminum, we don't care about that at all. You can disregard that fact. All we care about is that it is the 10th electron. Let's start assigning numbers to it then. So first off, we have N, or energy level. So looking at our electron configuration, we're at the second energy level, so that's an easy one. N equals 2. Next up, we'll start looking for the L. So our options here are either 0 or 1, saying that N is 2, so it's always 1 less than N. And in this case, 0 is representing our S block, and 1 is representing our P block. So since we know we are in the 2p6 position, we are in the P block, so that means our L is going to be 1. Next up, we'll look at our M1, or our magnetic number. And this can either be negative L to L. So in our case, it'd be negative 1, 0, or 1. So how do we tell this? We look at our electron numbers. So negative 1 holds electrons 1 and 2. 0 holds electrons 3 and 4, and 1 holds electrons 5 and 6. So we are at P6, it's really for the 6th electron, so we're going to take 1, meaning our M1 is equal to 1. Finally, our M2, or our spin number, it can either be negative 1/2 or 1/2, line up to electrons 5 and electron 6. Again, we have electron 6 in this case, so we're going to take the positive 1/2. Now we have everything we need, we just got to write them in order. So it's always N, L, M1, M2, exactly the order you find them in. So in our case, it would be 2, 1, 1, 1/2. And that specifically describes our electron scene here. So just a little bit of review here at the end. First thing we learned about today was orbitals and those blocks or subshells that the orbitals live in. So we have the S block that holds 2 electrons and has 1 orbital. It's a spherical orbital. P, which has 6 electrons and 3 orbitals, those 2 lobes and then the sphere. D, which has 10 electrons and 5 orbitals. And finally F, which has 14 electrons and 7 orbitals. Next we learned about electron configurations. Of course, that's when we went through each block and assigned an energy level to it, a block, and then, of course, the number of electrons. So, of course, we went all the way down with that. We have your S's, your P's. Remember, your D's come in at 4s2, and it comes in as 3d10. And remember, your F comes in down here after 6s2. You go to 4f14. Finally, we learned about quantum numbers. We learned about N, which is our energy level, which of course can be 0 all the way up to 7. L, which has to do with our block or a subshell. That can go 0, 1, 2 all the way up. M1, which essentially represents our orbital that we're in. And M2, which is our spin number that identifies our specific electron we are working with. That's all for today. Thanks for coming to the drawing boards presented by Tau Beta Pi. Have a great evening.